Hello everyone, my name is Abdul Mohammed Al-Radi, and on behalf of Cognitive Agents and Interaction Lab at the University of Dhaka, I am presenting the following on visual autoregressive modeling. Well, let's first get introduced to what VAR is, and I think it's important to answer these three questions before moving forward. First of all, what even is it? So, well, visual autoregressive modeling is a new image generation paradigm. Well, there are diffusion models and vision transformers and GAN, generative adversarial networks, etc. These are all image generation models, and this is just yet another image generation paradigm. And what's so good about it is, in terms of some metrics like Frechet inception distance, it's lower than the lower bound itself. Well, the lower it is, the better. And right now, as you can see in here, this image, let me turn on my laser pointer. So VAR is performing better than the FIT lower bound itself. And also it's 20 times faster compared to the diffusion transformers. So okay, so it must be something worth looking into. And so what can we do with it? So this actually exhibits a very good zero-shot generalization, which basically means it has a very good understanding of images itself. So it can perform some tasks like in-painting and out-painting pretty well. All right, so let's first talk about what autoregressive modeling really is. And well, autoregressive modeling is something that all LLMs use in transformers, and it is basically a technique that uses causal inference. And causal inference, what I mean is we sort of try to predict the next token or the word given all the tokens we have encountered before. So let's say that we want to predict the word apples in this sentence. So we should have these words ready for us, or their tokens ready, right? So this should, the culmination of these things should give us a reasonable probability distribution of apples being the next one, right? And this is great for texts because we also think like that, or we also speak like that. This is how speech is modeled, that we would want the next things we say to relate to the things we have already said. So, but if we wanted to use them, this LLM or the transformer for anything that was vision related, we had to make some adjustments so that images could translate into one-dimensional data. And we all know that this is inherently a problematic thing because just how speech is one-dimensional, image is not. Image is a two-dimensional signal. So let's see the parallels that we have drawn, that transformers for text versus transformers for images. So for LLMs, a single word is translated into its dictionary number or index. We basically look up the word in a vocabulary, right? And that vocabulary number is then corresponding with a learnable vector representation. And what that basically means is that a vector or a list of numbers basically is sort of trying to represent the word itself. And for vision transformers, what we do is we use a 16 by 16 patch of the image itself and we flatten it. So these are the pixel values. So from top left, so left to right, from top to bottom, we basically linear project this entire 16 by 16. So 16 by 16 becomes 256 size vector. And then we try to project that into some learnable vectors. And for LLMs, we add a positional embedding vector to understand its position in the sentence. So basically, if we have a word dog at the start of the sentence and dog in the middle of the sentence, we would want to add something to that vector representation so that they're not identical. We want it, we want to understand where it is on the sentence, right? So for VITs, if we have to understand where its position is, it's a little bit more complicated, and they used fancy things like rotational positional embeddings, because if you look at this top left part and the bottom part of this image, in the image they are very close together, but in the linear projection they are pretty far from each other, even though in the original image they're pretty close together. And also some things that don't make sense is this patch and this patch is adjacent, but in the original image, it's one is on the top right and the other one is in the middle left. So we can see that this is one of the research gaps that the researchers of VAR have pointed out that this is problematic. So let's elaborate a little bit further that what's going on here. So the key intuition behind this paper is that if we use autoregression, so we can simply uh, think of these three patches should be able to predict the fourth patch, and these four should be able to predict the fifth one. But we can see that there is no relation between these three and this one, other than maybe some relation with this one. So basically, and even if no matter what, we're always trying to learn an image from the top left to the bottom right. it's it is actually pretty good still, but we intuitively this makes no sense, right? Because image is a two-dimensional signal, and what does make sense, however, is if we have this middle portion of the image, and if we grow it a little bit on all the dimensions, that would make sense because there's a causality that this image can be expanded and sort of like a generative field, right? So this was one of the key intuitions behind this paper, because instead of using like next tokens, this paper proposes we predict the next resolution. So this is a transformer that they're using, which starts off with basically a one by one. Uh, let's just call it a one by one image, and then it tries to generate a two by two image from it, or a four by four, and then using those that one by one and four by four image, it tries to create a nine by nine image, and using all of these, it tries to create something like that, and ultimately the final resolution. So this makes sense because this is growing in both the dimensions instead of just going from one dimension. It's growing in two dimensions. This is the old one. The nine patches are all flattened, and that's how it's working. So we can see that they have given us this very interesting intuition that if we use instead of tokens, if we use prediction of resolution, then that one dimensional causality actually makes sense instead of whatever this is. And the other thing is this tokenization thing that we did was flattening a 16 by 16 image is also very bad, because how can we simply say that flattening a 16 by 16 patch is a very accurate representation of what information this patch actually entails, right? So for that, they use a very simple but very fancy name of a model. It's called Vector Quantized Variational Autoencoder, or VQVAE. So we'll first discuss about the VQVAE and then we'll talk about the transformer itself. Okay, so what is a VQVAE? Well, it's basically an image to image generation model. So first, let's say we have a picture of a dog and we use an encoder or a convolution. So this is basically going to be some height times width times 3, right? And uh, I think I can turn on the pen, like, okay, so height times width times c, right? And after that, uh, after some convolution operation, we're growing the channels and reducing the dimensionality. So it should become something like an h prime by w prime by c prime. So, and we know that, let's say, this slice or this vector is sort of capturing, let's say, this part of the image and projecting here. So this is what we call a feature space. I have to keep that in mind, that this is called F, or the feature space. This is a very rich representation of this image itself. So what they basically do is first they take these feature vectors or each of these slices, right? And then they look up on a vocabulary of vectors already existing of the same dimension, of course. In this dimension, it's the same as this one. So what happens is, uh, they find uh, the vector that's the closest distance. We use Euclidean distance. So the find the vector that best represents this particular vector and save its index into this matrix. So if this was h prime by w prime by c prime, this is going to be only h prime by w prime, because there is no this basically the entire vector is represented by the index. So 1 basically means this one, 2 basically means this one, and 53 basically means the 53rd vector. So this code book can be confusing, but this code book itself is what's synonymous with a vocabulary in LLMs, right? This is our dictionary basically. So then what we do is we use these vectors instead of these vectors, these continuous vectors. We use these discrete vectors. By the way, this is called a quantization, or Q, quantization, and this is basically we're looking up the vocabulary to build another feature space. Is another feature space, but this one is purely built out of this code book, right? And then we're using the decoder of another CNN to generate the image. And now if we the target output should be the input itself, because why not? Because we're trying to enrich this vocabulary so that it represents parts of images very well. So when we calculate the losses, these code book will get better over time in representing portions of images. Right? So yeah, let me turn on the laser pointer again. All right. So how does the VQVA work in their thing? By the way, this VQVA, the way it works, the VAR paper doesn't work like that. They actually create way more tokens than a standard VQVA. But this is what a VQVA does. So let's start with the multi-scale VQVA, or we will try to create all the encodings in a single run. So the input here is the image IM, and these are the hyperparameters. So let's say K is a hyperparameter, and HK, WK is the height and width at resolution scale of K. So I think it's very simple to imagine it like this, that the smallest scale is 1 by 1, the next scale is 2 by 2 or like 4, the next scale is 3 by 3 or 9, etc. So these are the scales of, and the final scale is the original resolution itself, right? So firstly, what happens is, this is the feature, E of IM. We're just uh, figuring out the feature space. This is something that can be easily done, right? So the feature space is calculated first, so that's the image, and then that in the next step we first let's look at the inside function of line 5. So interpolate f hkwk. So basically what that means is interpolation can be downsizing or upscaling. It can be anything depending on the input parameters. So I'm pretty sure this feature space is much bigger than the first scale. So definitely on the first run, the feature space, or this feature space which was h by w by c, will get smaller. It will become 1 by 1 by c. So this whole cube will just become a single log, and hopefully it will have enough information, rough information about the image itself, right? And then we apply Q to it, which is basically quantization. And if you apply quantization to it, basically instead of this one slice, we'll just have one index itself, right? So instead of 1 by 1 by C, it will simply become 1 by 1 by 1. And if we talk about, if the scale was 2, then instead of 2 by 2 by C, it would become just 2 by 2. So these are the token maps that we're talking about. So these tokens are basically sort of like the indices for looking up the vocabulary, right? So anyways, moving on. So then, since we do have this square, we can sort of generate the feature space from the codebook, right? So we look up and we generate this, and then we upscale it to the original size of the picture itself. Then the interesting part is here. We will subtract the phi of the output from the original feature space. Now, why are we doing this? So zk at line 8 is simply an image, and phi k is basically k amount of convolution operations, so that the dimension of f and phi of zk matches. However, what this line is simply saying is, for the next scale when it happens, I want you to try to predict the difference between the original image and the predicted first image. So this is what this is basically modeling residual images. We're not trying to all the scale in all the scale, we're not trying to understand the image itself. On the first scale, we are trying to understand the image. On the second scale, we're trying to understand the difference between the image and the first scale. And on the third, we're trying to understand the difference between the second image, basically the image and the error of first and second scale. So that's how the residual mapping is working. So this phi of k is also accounting for upscaling, and there's a data loss related to that. That's not very important. So this is how it looks like, sort of. Yeah. So R1 is just one token. R2 has 4 and R3 has 9. So basically, uh, this looks flat, but it's not. These are the 4 tokens, and we call this a token map. Instead of a singular token, this is a token map, because we are instead of, like, say, one token generating another token, it's more like one token generating 4 tokens, and there was 4 tokens and one token generating 9 tokens. So instead of a token, it's a token map, and it's pretty evident from this image how the tokens are expanding in 2 dimension. That's why that is, we can't just work with a uh, one token, we have work with a token map. So how does a decoder work? So let's say we have good understanding of all the uh, VQVAs, and we have saved up all the token maps into this one, right? So now it's almost the same in terms of everything. The input here is basically the set that we have just created from the previous slide, right? So this empty set was filled up with the token maps R1, R2, R3, etc. And we will use, first of all, our feature space will now only contain zeros, right? It's just a nothing. And for each of the resolution, first of all, we will look up the uh, token map, and then we will generate the feature space, and then we'll interpolate, and then instead of subtracting, we're going to add the phi. So what this basically means is, all the in all the resolutions, I'm sort of learning the residual image uh, subtracted, like the residual image subtracted from the original image. So if I add up all the residual image, I'll ultimately get the real image itself. So if I decode with the normal CNN, I'll get an image, I am hat. So I am hat is going to be our prediction, right? Okay. So this is the loss, the original input image and I am hat, right? And also the feature space difference and the perception loss and some other loss. I forgot about it. But this is basically the training phase of the multi-scale VQVA. So after the training, this was trained on ImageNet. So what happens is it becomes very good at generating these R1, R2, R3, so that after interpolating, it creates good feature space. Ultimately, it creates good images. So that's general difference between a normal VQVA and their multi-scale VQVA. They're generating a lot of tokens instead of one token for each scale, right? Okay, I want to zoom in on this picture because I wanted to show you the some interesting properties of this this 1D causal inference, right? So this one by one has capacity to produce this two by two, but this top portion of this R2 and the whole R1 is sort of responsible for the top left portion of R3. And this portion is sort of responsible for the top left portion of R4. And this portion is sort of responsible for the top left of the final one. That means if we project a ray, we can see that if we have all of these ready to go, then we can use these in parallel to construct this one. And this parallel processing is also why this is 20 times faster, right? Okay, so how do you train the transformer, right? So we have the start token, and this R1, R2, R3 with 1, 2, 3, 4, 1 to 9, these are all the ground truths. This is the output of our VQVA, and we also have the same thing at the bottom, right? The VQVA outputs. So we have a start token, and we feed it through the transformer, and hopefully we create a R1 hat, right? And R1 hat is our first token. All right, so and then we use our actual R1, which only has one token, right? So because it's a scale of 1 by 1, so we use word embedding and up interpolation. What this basically means is we first translate R1 into the lookup table that we used. So instead of just being an index, it will become E1, right? So let me go back to the deconstructor. So basically, it was here R1, and it will become E1, which is the feature space thing. So E1, and then instead of just keeping it E1, it became E1 through 4. Like R1 became E1 through 4. Then that's because of up interpolation. So because just as the input of the transformer, we want that the transformer model understands how to expand from a lower resolution to a higher resolution. So let's say this R1 is basically up interpolated into 4 tokens and the start token. These two are used to create the R2 itself, R2 hat, right? And then R1, R2, and the start token. These three are used to create, my bad, a start token, R1 and R2 is used to create R3. And all of these are basically predictions, and all of these are ground truths. So basically, if we have just simple cross entropy loss, then we can train it. And also an important thing to notice here is that this block and this block, like when we try to create the attention map, we would want to mask out these parts because we don't want E1 to know what E2 is, which is basically a simple causal mask, where it's also very common in standard transformer training when there is we have to predict, we don't want to look into the future, right? Right. Okay, so what is zero shot generalization? It's very good at it. Zero shot basically means it was not created for this task, but it just performs very good at it anyway. So there are two types of downstream tasks that we have tested. They have tested. One is in painting, one is out painting. Uh, if it's in painting, then this part of the image was actually occluded and given into the var model, and the output was these generated ones, right? And out painting is basically this was the original image, and it painted outside of the borders. This is showing good generalization, considering this was simply made with ImageNet dataset. So here are a few ideas that can be used. Well, first of all, we have to test VAR's zero-shot deblurring capabilities. Right? How good is it in just deblurring in general? And if it's not that good or whatever it is, we also have to try to fine-tune the VAR transformer. We don't need to touch the multi-scale VQVA because it's just all it does is tokenize images, and the tokenization we don't want to touch. That's fine. But if the ground truth is a sharp image and the input tokens are blurry, then hopefully the transformer learns how to remove the blur. And if this preliminary fine tuning, if it works, we can work on multiple data sets to create a better image deep learning model. All right, thank you very much.